Okay, so let's talk more about the complex numbers. Excuse me. So, here let's actually introduce the symbols for complex and real numbers. So, real numbers, the symbol is this R, and complex number, the symbol is this C. So, the formal definition of a complex number is that if, well, okay, so if it can be written like a number z can be written in the form a plus bi, where a and b are both real. Okay, a and b are real. Remember, are real. Okay, so they belong to the real numbers. This means that they are real. Okay, it's just quite fancy notation. Then z is a complex number. So actually, the previous some videos I remember I talked about the complex number being the real part and imaginary part not equal to 0, and this is not very correct. And the fact is, a and b can be 0, so I'm sorry that I actually misled you all, but let me declare here, they can be 0. Okay, they can indeed be 0. So in fact, I can say that the number pi is actually complex. It's actually complex. And why? Because I can write it as pi plus 0i, right? And that is of the form a plus bi. And 0 is actually a real number. Pi is also a real number. Therefore, pi is actually complex. Therefore, any real number is also a complex number. Alright? This is one important thing to remember. So, with that being said, let's take a look at the property of our imaginary units I. So, I squared is -1. That is by definition. And actually, definition. Okay, sorry, my spelling is so bad. And actually, it follows the basic rules of algebra. Say, I cubed is just I squared times I. Okay, it follows this rule. That is I squared times I. Okay, so I squared because it's -1, so -1 times I is -I. And if you just keep on going, you find that I to the 4th power is actually I squared times I squared. Okay, so you just combine the powers, and I squared is -1. So -1 squared is just 1, or you can do I cubed times I, and simplification is also getting you a +1. And I to the 5th power, I to the 4th power times 1 times I. So I to the 4th power is just 1, so 1 times I is I, and you cycled back on itself again. So I to the 5th power is I to the 1st power, which is I. Therefore, you see it's going to cycle around and around, and just like -1. So -1 squared is 1, -1 cubed is -1, and -1 to the 4th power is 1 again. So it also cycles, but for I, the cycle is much longer. You see, it takes 1, 2, 3, 4. 4 iterations to get you back to I. Okay? Now, that is the strange property of I. Excuse me again. Here, we have a property of the complex numbers. So basically, it's saying if a plus bi equals to c plus di, then a is equal to c and b is equal to d, which makes sense, right? Just to say that the corresponding real numbers are the same and the corresponding imaginary components are also the same. Okay, that's fair enough. So let's do an example actually. First of all, we have the addition. addition and subtraction. So we just manipulate them for these two operations for now. Say I have 3 plus 4i. That is a complex number, plus negative 5 minus I. Then what is it equal to? So what you do is you combine the real parts and you combine the imaginary parts. So I'm just going to open up the brackets and collect the real parts and imaginary parts. We have 3 minus 5 is negative 2. 4i minus I is 3i. So this is the answer. And yeah, subtraction is more or less the same. So I'm going to use the exact same example. 3 plus 4i, this time a minus negative 5 minus I. So again, break the brackets and we get 3 plus 5 is 8. 4i plus I is 5i. So this is our answer. And well, just to give us a better geometrical interpretation. Okay, this is real and this is imaginary. Two, 4, 6, 8. 2, 4. Okay, good. So our first number is 3 plus 4i, so it's a point probably somewhere here. 3 plus 4i plus negative 5. Okay, fine. Wow, my color is very inconsistent. Negative 5 is somewhere there, and minus I. Okay, so if we add these 2 points together, we get negative 2 plus 3i over here. So, well, what does that mean? Let's draw the lines connecting these points. And actually, hey, you see, it's like forming a parallelogram. It's really like forming a parallelogram. So if we have 2 complex numbers adding together, it gives you the other side, I mean the other point of a parallelogram. And wow, that is quite magical. As for the minus operation, let's also quickly do it. So 3 plus 4i. Okay, again, it's this point and this point, but when we minus, we get 8 plus 5i. So it's somewhere here. And again, if we were to connect these 2 points, we get something that doesn't make much sense. But then, if you move this over here, extend it, and of course my extension job is not that good, and you can connect it again, you'll find yourself a parallelogram just again. But this time you see it's in the opposite direction, and it's giving you the longest side, right? And how is this happening? It's actually same to addition just because you're subtracting. So subtraction is a part of addition. It's just equivalent to adding a negative thing, right? And that's why it gives you the parallelogram in the opposite direction. Okay, and hope this helps you and this inspires you. Next time we'll do some multiplication problems.